This video will focus on Dalton's law of partial pressures and several of its applications. Part of what Avogadro suggested was that the actual identity of a gas doesn't really matter when describing its gas properties, like its pressure, its temperature, its volume. Equal amounts of hydrogen and oxygen, for example, would behave the same under the same conditions of pressure and temperature. It doesn't even matter if you're talking about a pure gas or a mixture of gases. So when you have a mixture of gases in a container, the mixture's properties are just the sum of the individual gases' properties. In this illustration, the blue gas exerts 2 units of pressure all by itself. The 2 weights on top are used to represent units of pressure. The red gas exerts 5 units of pressure. If they're in the container together, the total pressure is just the sum of their individual pressures. So 2 plus 5 equals 7 units of pressure. And that's always true. The total pressure of a mixture of non-reacting gases is just the sum of their individual pressures. And it's called partial pressure when it's multiple gases in the container together. Partial pressure means the pressure exerted by one gas in a mixture. It's the same as the pressure that gas would exert all by itself. So when the blue gas is in the container by itself, it exerts 2 units of pressure. When it's in the container with another gas, the blue gas still exerts 2 units of pressure, and it's called its partial pressure because there's something else in the container. Look at this example problem. You want to fill a pressurized tank with air for diving. You want the tank to contain 50 grams of oxygen and 150 grams of nitrogen. Calculate the total gas pressure at 25 degrees Celsius. There's 2 ways to solve this problem. In both cases, you're going to have to calculate moles of the gases first. One way is to then calculate the pressure for each gas using Pivnert, then add the 2 pressures. An alternative is you can use Pivnert once with the total moles of gas substituted in for N. Either way works. I'm going to use the second method. Grams of O2 is 1.5625 moles. (150 grams of N2) is 5.3533 moles. I'm going to use Pivnert once, solving for total pressure by using the total number of moles. The volume given in the question is 4 liters. When I add my number of moles together, I get 6.9158 times my same gas constant times my temperature in Kelvin of 298. When I solve for pressure, then I get 42 atmospheres. This is a fairly common type of problem. You're given what's called a 2-bulb apparatus. Initially, the 2 gases are in separate bulbs. When the stopcock in the middle is opened, the gases will mix. Both gases will then have the total volume available to them. So how do we calculate the partial pressure of neon after mixing? First of all, it's important that you understand that neon doesn't care that helium is also present in the apparatus. That doesn't affect neon's numbers in any way. All that matters for this question is that neon has an initial volume and pressure. When the stopcock is opened, the volume available to neon changes, so its pressure will change too. Pressure and volume are changing. This is a Boyle's law calculation. P1 and V1 are the initial pressure and volume before the stopcock is opened. 0.850 atmospheres and 3.5 liters. V2 is the total volume of the whole apparatus, and we're solving for P2. So the partial pressure of neon turns out to be 0.54 atmospheres. This second part of the question is where Dalton's law comes into play. The total pressure in the apparatus after mixing is the sum of the two partial pressures. We just calculated the partial pressure of neon after the stopcock is open. So we just need to do the same calculation for helium and then add the two numbers. So helium initially has a pressure of 0.575 atmospheres and a volume of 2 liters. We're solving for its new pressure when it has the total volume of the apparatus. The partial pressure of helium turns out to be 0.21 atmospheres. So now, to get the total pressure, I just add the partial pressure of neon and the partial pressure of helium. Partial pressure of neon was 0.54 atmospheres. Helium was 0.21 atmospheres. So the total pressure in the container is 0.75 atmospheres. Dalton's law questions often include the concept of mole fraction. This is defined as the ratio of the number of moles of one component of a mixture to the total moles of the whole mixture. Mole fraction is represented with a capital X. So the mole fraction of component A would be the number of moles of A divided by the total number of moles present. This shows up in Dalton's law question because mole fraction can also be related to partial pressure and total pressure. This question asks for the mole fractions of nitrogen and oxygen in a gas mixture, given their partial pressures. To get mole fraction, all we have to do is divide each partial pressure by the total pressure. So for nitrogen, I would put the pressure of nitrogen over the total pressure and get 0.789. And for oxygen, its partial pressure over the total equals 0.211. Two things. First, mole fraction is unitless, so you just report numbers. And also, even though it's called a fraction, we report it as a decimal answer because we still have to use sig figs. So these are the final answers. The mole fraction of N2 is 0.789. the mole fraction of O2, 0.211. In this question, you're given the number of moles of each gas and the total pressure. You're asked to calculate each partial pressure. On a previous slide, it said that mole fraction of any component equals that component's partial pressure divided by the total pressure. So rearrange that and solve it for partial pressure. This shows us that the partial pressure of a component is its mole fraction times the total pressure, which makes sense because the partial pressure of a substance should be some portion of total, and it should be based on how much of the total sample is represented by this component. So to answer this question, we need to calculate the mole fraction for each gas first. So the mole fraction for neon, its number of moles divided by the total. Give us 0.6068. Mole fraction for argon, 0.74 over the total moles, which equals 0.1007. And for xenon, we put 2.15 over the total, for a mole fraction of 0.2925. Now, as this equation here tells us, all we need to do now is multiply each of these mole fractions by the total pressure of 2 atmospheres to get the partial pressure for each of these gases. So for neon, that's 1.21 atmospheres. For argon, it's 0.201. And for xenon, it's 0.585. A very important application of Dalton's law involves a lab technique for collecting a gas over water. We're going to do this lab in class, so make sure that this stuff makes sense. In this process, a set of reactants are placed in opposite ends of a gas collection tube, and the tube is filled with water. The tube is then inverted into a basin of water, at which time the reactants come together and completely react. The gas formed during the reaction is trapped in the upper portion of the gas collection tube. It would look something like this after the reaction was complete. The gas has collected in the upper part of the gas collection tube, and it's trapped by the water below it. Here's the only problem. When collecting a gas over water, you always collect water vapor too. It's impossible not to. So to know the pressure of just the gas from the reaction, we have to do some math to take out the effect of the water vapor. Atmospheric pressure is pushing on the surface of the water. Our gas and water vapor are pressing against the atmospheric pressure. So the pressure of our gas plus the pressure of the water vapor is equal to atmospheric pressure. But we want to know the pressure of our gas. So we rearrange this equation, and to calculate the pressure of our gas, we'd take atmospheric pressure and subtract out the water vapor pressure. Vapor pressure of water is known for lots of temperatures. You can look these numbers up in a table. Here's an example I found just by Googling it on the internet. In this question, a sample of oxygen is collected over water at 20 degrees Celsius and 738 millimeters of mercury. The volume collected is 310 milliliters. What's the partial pressure of the oxygen? For this part, all you have to do is use the atmospheric pressure and take out the vapor pressure of water at 20 degrees Celsius. Atmospheric pressure is listed as 738 millimeters of mercury. The vapor pressure of water at this temperature is 17.5 millimeters of mercury. So when we subtract these two, we find that the pressure of our gas is 721 mmHgs. The second part of the question asks for the volume of this gas when dry. So that means without the water vapor at STP. So what kind of gas calculation is this? We just calculated the pressure of our gas, and the question tells us that the gas is at 20 degrees Celsius and has a volume of 310 milliliters. We now want to know what its volume is at standard temperature and standard pressure. So it's a combined gas law question. We're going to use the pressure we calculated, the temperature and the volume listed in the question for one set of numbers. We're going to use standard pressure, standard temperature for another set of numbers and solve for volume. The pressure we calculated was 721. The temperature of the reaction, the volume of the gas was 310. The temperature was 293, because for gas law problems, we always have to use Kelvin. We're going to set this equal to standard pressure and standard temperature and solve for this new volume. The answer turns out to be 274 mmHgs. Previous question assumed that the water levels inside and outside the gas collection tube were equal. This is not always the case. The water levels inside and outside often are not equal, so we have to add another term to our calculation. That additional column of water means that atmospheric pressure was some amount stronger than the combined pressure of the gas and the water vapor collected. So now our calculation looks like this. Pressure of the gas is equal to the pressure of the atmosphere minus the pressure of water vapor like before, but also minus the pressure represented by that column of water. For this new factor, we have to translate the height of water into a quantity of pressure that it represents. Height of water is not a pressure unit, but height of mercury is. That's millimeters of mercury. So we have to convert the height of the column of water to an equivalent height of mercury. So we're going to set up an equality that says that the height of mercury times the density of mercury will equal the height of water times the density of water. The density of mercury is 13.6. The density of water is 1. We have the height of water and we want to calculate that equivalent height in mercury, so solve for the height of mercury. And this answer is what you're going to use for that pressure represented by the water column. Let's do this example. It says that carbon monoxide is collected over water. It gives us the temperature the atmospheric pressure, it tells us the volume of gas collected. Then it says a 72.8 millimeter column of water remained inside the gas collection tube. We'll have to include that when we calculate the pressure of the CO collected. To calculate the pressure of the carbon monoxide gas, we'll start with the atmospheric pressure of 754 torr. We'll take out the water vapor pressure, which is given as 17.54 torr. And then we also need to subtract out the pressure represented by the column of water. To do that, we take those millimeters of water and divide it by the density of mercury. That was what was explained on the previous slide. So 72.8 divided by 13.6 is our other factor. That part itself equals 5.35. So 754 minus 17.54 minus 5.35 gives us the pressure of our carbon monoxide gas as 731 torr. Then part B asks for the volume at STP. So again, we're looking at a combined gas law question with our calculated pressure, the temperature, and the volume listed in the question as one set of numbers, the STP values as another set of numbers. So we use 731 as our pressure. 268 milliliters is the volume they told us, and this occurred at 293 Kelvin. And we set that against standard pressure and standard temperature. The volume of this gas at STP is 241 milliliters.